So our first speaker today will be Professor Daniel Brandeis, who's a long-lasting friend of the Center, who's been here several times, and we're very happy that he was able to come again and to give us the lecture about the reading brain.
So first, many thanks to Svea and the Center for organizing this wonderful conference and for giving me the opportunity to present our new insights, some of our old insights, and really just our work and also our appreciation for your work here at this conference. The title is very ambitious, The Reading Brain, and you'll immediately see that I don't want to cover everything, and among the things that I wrote in this short abstract, I'll really focus on brain function, how brain function mediates reading, how reading develops in normal, typical readers, and in readers that become dyslexic readers that have a significant problem with reading acquisition. And I'll really try to give you a good impression of how these processes, these developmental trajectories are really embedded in the brain, and how understanding them will also facilitate proper remediation approaches and really get also at a deeper understanding of the potential and also of the limitations of plastic but developing brain. So the structure of, and by the way, I have to say that I really apologize for the contrast. I do have some color slides, and I say that now because you won't see much color. So, sorry, I cannot do anything about that. So I'll first focus on the brain mapping methods and the basic developmental aspects, and I'll go to reading specific development, reading acquisition, and also what you can do with early training, and at the end I'll focus really on dyslexia, the systems involved, and the predictions that are possible with our methods. In terms of neuroimaging, brain mapping, and that's why the title is called The Reading Brain, we have nowadays really wonderful methods that really display to us how the brain processes language, how we read, how we understand spoken language, and how we get these two things together. It's kind of important to realize that two of the most common methods, EEG-based imaging, if you do source localization, and then R-based imaging, are really not measuring exactly the same thing. They do have different strengths. EEG has the strength to resolve things that happen within a second or less very well. So we can detect many processes within a few hundred milliseconds and really distinguish them. But in terms of localization, you need many assumptions, while fMRI is a really slow method in the sense that it really reflects a delayed hemodynamic response to neuronal activity, but it excels at spatial resolution. So we can really look at distributed networks and their extent and really discover subtle shifts in terms of brain representation. And I think the important thing is that both aspects of resolution are relevant. So reading is not a process that really engages the brain in its entity and is synchronized together, but they're really distinct subsystems supporting that. And reading is also not a slow process. It really has to be fast. That's what we're talking about here. Fluency really has in its definition the part of getting things right within a certain time limit. And these resolution to do things, understand words within less than a second is really critical. That's what reading is about. So it's not luxury what we're doing if we have two methods and if we try to combine them as I showed you. Usually the methods converge, and the idea, the concept is really we combine these methods, or we look at both EEG and MRI-based results, because we think that, shown with this movie, that essentially what we depict here with some spatial detail, the networks activated during reading words are really activated sequentially. As you see in this movie, this is the same group of subjects, the same paradigm, and you see essentially that there is an activation sequence from the back to the front, and there are stable epochs, there are epochs of transition, so you get the full dynamics and the spatial resolution. So the methods are really complementary and converging, but I also have to say that's not always the case. There are some cases where the methods diverge, and let's keep it at that simple stage. So you see the distributed networks displayed here for children, adolescents, and adults, mainly in the left hemisphere. And you see frontal and temporal activations patterns that are kind of stable across this developmental groups. And you see that the EEG source localization within the same children, adolescents, and adults with the same paradigm do show you a different type of specialization for word, not the language network with the frontal parts, but mainly the occipital temporal regions. The other thing you see with the EEG is this, that the activity becomes faster. This is a time scale. These are the children, the blue ones are the adolescents, the black ones are the adults, and you see you have a timing change. Children are slower with their word-specific processes than adolescents, and these are slower again than adults. So if you just try to summarize what we see here, kind of stable spatial representations, speeding up, stable representations of some partly different things, but again, stable over development once you've mastered initial reading acquisition. Essentially, this leads to a model where we think that initially the network is formed quite early, delineated spatially, but then within this network you still have lots of fine-tuning, lots of specialization, and lots of becoming more efficient. Okay? And that's essentially what, after initial reading acquisition, leads to fluent, fast, efficient reading. I also want to say that essentially these word-specific findings have to be seen on the background of typical brain development. The brain is not only developing when we're doing reading tasks, the brain is also developing at rest. Our resting state functions are dramatically developing, and this is from some work showing you that essentially if you look at the same age groups, children, adolescents, and adults, you see dramatic changes in brain function. With eyes closed, lying in the scanner with your EEG cap on, what you see here is that slow waves displayed here under 3 Hertz are really decreasing in amplitude dramatically. You see that deployed here. And what we showed is also, if you look at a fMRI signal, the bolt signal, the same wave, just power of the fluctuations. You get the same curve and you get a linear relationship between the two. And you always have to realize that there are many things developing, and reading acquisition and specialization for reading, tuning for print, tuning for linguistic expertise is just one aspect of development. So how do we learn to read if you look at it from a brain point of view? The model is, we know from lesion studies, we know from adult literature, that there are some regions that are really critically involved in bridging the gap between visual input representing language and auditory input representing language. We have a visual system, we have an auditory system, and somehow learning to read means that we have to map essentially letters, shapes onto our existing language system, and we have to be able to print them, write them in a way that we do it with language stimuli and not just with drawings. And this major step, we have the skills to differentiate visual stimuli acquired very early. We have language also acquired very early, typically. We can speak at the age of typically 2 to 3 very well, but reading is really building on this language functions. And this is a major step, and I think it's a major form of plasticity. So if you look at that with a dynamic view, we've seen a movie representation of this yesterday. Essentially what you see is at the beginning, if you have visual input or auditory input of the same words, obviously the visual input comes in through the visual region, the back of the head, the auditory input, the auditory cortex, but at around 300 to 400 milliseconds, both inputs converge onto the language system. And this is essentially what this model should represent, how this convergence is really implemented in the brain. Now, we have started doing that with event-related potentials, with electrophysiological activity, and one of the findings, actually from a colleague in Israel, data here, Shlomo Lenkin, this is data from California group. They have shown that a very, very long time ago, actually more than 20 years ago, that you get some core specialization in a visual event-related potential around 200 milliseconds or 150 milliseconds in skilled adult readers, which essentially is represented by a larger occipitotemporal activity, larger event-related responses over left occipitotemporal regions to word-like stimuli as opposed to visually matched drawings. An interesting thing is it's not specialized for words, but it's also specialized for things that really look like words or pseudo words, but also shapes that are really very close to letter stimuli. Now, if you want to really look at reading acquisition, you need a paradigm where you can really probe reading at a time when children cannot yet read. So we used an implicit reading paradigm. This is a German word, this is another German word, this is a repetition of the German word, and children just have to press for the repetitions. This is a task that a child that cannot read can do very easily. You do the same thing for the pseudophonics, and you immediately realize that the same task, detecting immediate repetitions, is much harder for us, for the pseudophonics, because we don't have the sufficient representation and don't detect repetitions immediately. So this is a very, very simple paradigm with which we can probe emerging reading acquisition. We know what is shown here, that we have this left occipitotemporal response, negative blue here, which is much stronger for words than for symbols. This is the difference representing kind of the specialization for print. And what we found is that in kindergarten, Switzerland children are in kindergarten till the age 6, you don't see any specialization for print. So these children really treat words and symbol fonts the same. So these conditions are the same for really non-readers. Even though they're already quite a bit exposed to print. If you ask them which is print, more than 95% of them say this is print and this is not print. So the familiarity, the visual familiarity is there, but that's not sufficient to elicit this print tuning response, even though they have seen this type of pattern much more than this type of pattern. Okay? Now the question is, when does this print tuning emerge? And there are different hypotheses. One is that it's a slow process that takes a lifelong, and really it's a matter of expertise, that you're learning and learning and getting better and better and better, and then actually you're improving with reading until late adolescence at least. So it could just mirror kind of our skill curve. Or it could be something that really reflects the link between the graphemes and the phonology. Something that really is acquired right at the beginning of reading. And the answer is relatively clear. We see that after 1.5 years, we have a huge difference. And if you look at the difference, it's even larger than in adults. So it seems to be some sort of what we call print tuning, which happens right at the beginning when you really learn to read, and not when you become really fluent. Yes, by the way, these are source localizations showing you that this really does localize to left occipital regions. A bit blurred, not as focused as with fMRI, but now let's look at a bit later, at the development a bit later. Okay, are now children age 10 year, adolescents age 16 year, and the adults. So what happens in between, right? Once you have established essentially this basic print tuning. But the really interesting thing is that you can see that this overall activity reduces. The colors get less dark, that means less amplitude. The difference is still highly significant with the lower amplitude, so that's what counts. And the localization is still very similar, left occipital regions. Here, that's a smaller group, so it doesn't become quite as significant. But essentially, you see what I told you before, kind of a very stable spatial representation of this response over essentially the 15 years. It's a cross-sectional study, but I think it's more informative regarding stability of the networks involved in this porous print tuning. And the other thing you see is really this timing change. They get really by nearly 100 milliseconds faster from age 8 over age 10, 16 to 25. And that's a lot. I mean, essentially, adult readers have this response at around 150 to 170 milliseconds. And if you start with 250 milliseconds, so that's a change of around 30%. That's huge for a process. Now here again, the contrast of this is what you see if you compare words to these symbol strings, contrast them and integrate them over the whole analysis period, the whole period when the words are on and also when they're off. And this is the same contrast with fMRI. And you see really very different patterns. You see prominent occipitotemporal print tuning mainly with the EEG. If you do a region of interest analysis with this type of data, you also see some print tuning in some regions, but that's not the biggest thing you see. And that's why we think that multimodal approaches are so important. Not because they convert so wonderfully, but because they really show you different aspects of reading. Now, we talked about development of reading and arguing that this kind of coarse print tuning is happening very early, right, during the first 1.5 years in school. And afterwards, it just has established its network, but becomes faster, more efficient, and is performed with less neuronal activation. But actually, if we say this print tuning happens very early, does it really need reading? Right? I mean, what we've shown is that essentially the association between in kindergarten, before they've been exposed to formal schooling, reading training, they don't have this print tuning. After 1.5 years, when they're basic readers, they do have very strong print tuning. And what they have learned is essentially the alphabet, the graphic phoneme correspondences, and reading for meaning. So we really don't know which aspect is really causing this print tuning. And that's why Sylvia Brame and our group, together with Heikki Jytinen's group in Finland, designed a study where we looked at kind of the brain correlates of early graphic game training, graphic phoneme training. And that's all happening at age 6 before these children enter school. And the design was kind of balanced crossover design. One group started with the graphic game, had a numeracy game as control afterwards. The other group started with the numeracy game and had the graphic game, graphic phoneme training as the critical intervention. So you have a control period for both groups, and we have EEG and fMRI post-training 1 and post-training 2. All before the end of formal schooling, all before they really learn to read from me. It's 8 weeks training, and the result of this training is published. It is quite impressive that the children were first behaviorally much better at identifying letters, and this is the control condition. They also get a little bit better by playing exposure with letters. They draw their birthday cards and things like that, so they do learn something, but far less than if they are trained with the graphic game. So there's a significant correlate and a significant interaction. Let's look at eventual potential correlates. And essentially what you can see is in this bit complex graph that this left occipitotemporal response is already there to all the stimuli, to the false one stimuli, and to the words. And it starts differentiating over the 3 time points we've measured. And essentially the graphs show you it starts differentiating when you have the training, and what's training is when you do the control training, there is little change in this region. I think that's a bit better displayed in the maps. These are the maps seen from top. You have no specialization before you do the training. After the graphical game training, you have a very prominent left lateralized specialization. When you switch over to the numeracy game, actually part of this specialization decays. And it's the other way around for those who have the numeracy training first, no change, and then a strong change once you get that graphic phoneme training. And if you do the source localization, you get right to this left occipitotemporal region. Where do you see print tuning with real reading acquisition and real schooling after 1.5 years? It's slightly posterior, but it's overlapping with this region. If you look at the fMRI pictures, essentially it seems like a complex picture. I'll just guide you through the critical thing. Essentially here, you look at collapsed over 2 groups before the graphic game training, after the graphic game training. What you can see is essentially at the beginning, you have more activation in blue for pseudophons than for the letters and for the words. And after the training, yellow, you have more activation for the word lag or words. And that's not happening in a control game. Okay? So you have a very nice left occipitotemporal, also a bit right occipitotemporal training effect in the fMRI, converging with the EEG source localization. Okay, so essentially if you put those together, that's the fMRI activation pattern, the word versus symbol difference, pre-post training difference, and that's the same for the EEG, and that really converges. So we can say this type of course print tuning is really reflecting not reading for meaning, but really the graphic phoneme association that has been built, and it's really reflecting left occipitotemporal activity in this early time window around 2.5 thing you see from a more practical point of view is that these results are very nice, but they're based on 16 children. These results are also very nice. They're based on 32 children. This simply represents the fact that if you have 3 successful measurements in the training paradigm with 6-year-olds, then not everyone will complete the study. So you lose about 50% of the children. Not for a single session, but if you have to have 3 good fMRI sessions during the course of the training. At least that was the case in our studies. So, let me move to not normal reading acquisition, but to dyslexia. And we've heard a lot about brain representation. I think what is important for me to start, although I'm focusing on the visual word form system and I'm focusing on print tuning aspect, I think it's important, and you will see that all the time again, that it's not only this region that is making the difference between children who cannot properly learn to read and develop dyslexia and children that do not have this problem. And some of the differences are also in a way, in a direction that dyslexic children have no brain activity. That's kind of displayed here, more frontal activity in some regions. Okay.
Sorry, Daddy, can you go to the mic?
Okay. Sure.
Oh.
Oh. Thanks for telling me. Okay, so I tried this way. And you tell me again, right? Okay, you see the definitions. You see also the DSM-5 definitions of dyslexia, which is no longer called dyslexia. But I think what is really important is there are many, many models. People still agree that phonological processing is at least important, but there are many alternative models, and Ken has listed them extensively. I also want to say something about audiovisual processing, but it's really important that there are different approaches to understand this type of disorder. I also want to mention that there is not only brain function and brain connectivity reflecting the problems that you have if you're a dyslexic reader, but there are also structural findings. We've heard some about these structural findings. I'm not going to go into detail, but essentially they're also converging some, usually on the same regions that are critically involved in dyslexia. And I also want to mention that there is a strong familiar genetic component to dyslexia. And so far what people have found is very small, but converging effects on neural pathways that have to do with neural migration. And there are also some imaging studies showing that groups with a certain genetic variant, groups who are at risk for dyslexia, do have a different brain activation in reading tests. In this case, you see this increased frontal activation that can be one typical marker of dyslexia. And this is something which shows you that many candidates are around and few more or less significant effects are around. And in our study, despite a really large sample of more than 1,000 subjects, we didn't get anything that was juvenile significant. So, if you go back to the neurophysiology and to this basic print tuning, what we can see is that essentially what I showed you before, this print tuning occurs when you go from kindergarten to grade 2. Is it better now with a much better? That means you missed the first part. Sorry. Okay. You see this dramatic print tuning is essentially reduced to less than a half in the group that develops dyslexia. Now we have this group developing dyslexia because we selected children at risk for dyslexia, otherwise we would not have had such a large group with such a small study. But essentially what we can see immediately is that this type of course, print tuning at the beginning of reading acquisition is really dramatically impaired in the group that develops dyslexia. We've then followed up this group for after another 3 years, and we've seen that essentially this prominent discrimination response between the two stimulus classes becomes less prominent, also statistically. Probably because in grade 5, if you're a typical fluent reader, then this differentiation is not so important anymore and can be done with less neural resources. And we've also seen that if you look at the N1 component, that this marker of print tuning, that dyslexic children seem to catch up regarding this marker only. They still have their problem, they are still slow and impaired reader, and they are still diagnosed as children with dyslexia. But this aspect is no longer critical. And this is just illustrating to you how strong these responses are in 2nd grade. This is not that we selected these maps because they are particularly nice, but because if you go through the whole time course of print processing, this is really the major event in 2nd grade in terms of amplitude, what you do with the words. So this seems to be really the developmental stage where you really putting all your neural resources into print processing and differentiation. And when we're looking in 2nd grade, this is again a representation with just inverted colors, but showing the same significance in terms of a large difference between the two groups in terms of print specialization. 3 years later, this is no longer significant. When we look at the fMRI, in the same children, in the same groups, it's also no longer significant in a whole brain analysis if you look at the occipital-temporal region. If you do go into a region of interest analysis, you still find this pattern, but it's not the most prominent thing. So in this sense, EEG and fMRI converge in telling you there is a change of what has been very important in 2nd grade is no longer so important, and no longer so many resources are invested here in 5th grade. So we did 2 things. I mean, one thing was we thought maybe we're really unlucky. Maybe we're catching some developmental course where there is a major lag in the dyslexic children, and with 5th grade, maybe we're just catching a time point where they really show the same activation pattern, but 2 years or 3 years later, that's differentiating again. But we did not really believe into that, so we also did different paradigms. Here the result of this follow-up, essentially the same pattern, no discrimination, neither in the full brain fMRI analysis at age 15 nor in the EEG analysis. And this doesn't mean, I'm showing this slide, this doesn't mean for Zvia's group that no adults with dyslexia show print discrimination deficits. In some studies, in some definitions of dyslexia, I think they do show them very well, but not in our groups, not in our paradigm. So when we looked at reading in this group which still had behavioral deficits, we looked at more complex paradigms, for example, pseudo-homophone reading. I'm just trying to show you one result that I find particularly impressive, and that also illuminates a bit the role of this visual word form area, this left occipital-temporal region. Our connectivity analysis in a paradigm where they really had to do more than implicit reading, where they had to do explicit reading and very deep phonological processing, showed that in essentially control children, this visual word form activity connected to the whole language system. And this connectivity was essentially absent in children with dyslexia. So this visual occipital-temporal region is not doing reading, but it's making the link to the language system. And you can visualize that very well with this connectivity analysis. This is the group difference we could really say that for this specific region, you really have a major significant difference in how the two groups connect to the language system. So if you go to a more advanced task and connectivity analysis, you still see these deficits. We also went to sentence reading paradigms, and because of time constraint, I'm not going to go into detail with that, but essentially this is a classical paradigm comparing children with dyslexia to chronological age-matched groups, so same age, and to performance-matched groups, which are younger. And what we found is essentially there are a few aspects that really are specific to dyslexia that really are seen when you compare them against the age-matched group and against the performance-matched group, and that's essentially basic word processing activity, both in the EEG and its FNRI representation. And these are not the differences you get if you look at semantic processing. Semantic processing is impaired, but not different from a developmental delay. So that's very similar to children who are just younger. We did another twist. We thought maybe the limitation is that with our very simple paradigm, one word every second, we're not really challenging the reading system of the older children, age 16. And we did essentially a very rapid reading paradigm, a rapid string processing paradigm, where essentially every 300 milliseconds we presented a word. So that's a reading rate of 200 words per minute. That's much faster, right, than 1 word per second. And actually the result is here that you do get you do get differences. You get significant group differences, and you do get them now again in a whole brain analysis in the reading network, including the left hemisphere reading network, including the left visual word form area. So if we do challenge the system properly, then we see the deficit again. And we also did with this group an audiovisual paradigm, because this is another hypothesis that there are basic problems with bringing together auditory and visual information. This paper is still under review, so please don't take pictures, don't send them around. But the core message there is, if you look at audiovisual processing, this is shown, I think, very nicely here. Audiovisual stimuli activate auditory and visual regions, obviously. What you do see in terms of group effects is, one, a major group effect that children with dyslexia just have more frontal activity to do this audiovisual matching task. And the other thing is that you get into left hemisphere reading specific networks that are less activated if you look at how they respond to longer stimuli that have to integrate audiovisually, not for single letters. So that's the interaction between stimulus length and group. So then you're again back to the deficits that you see. We've also looked at the possibility to predict essentially reading abilities with responses measured before children learn to read. This is showing you a prediction story with essentially speech sound mismatch responses that are strongly left lateralized in those children that become good readers, and less left lateralized, even right lateralized in those children that become poor readers. And we can do quite a reasonable prediction, better than with all the behavioral measures we have, with this mismatch activity measure from kindergarten. And that's really true prediction. Brain activity from kindergarten, predicting reading skills in 2nd grade. Many people talk about prediction and mean they can discriminate risk groups, or they can discriminate different trajectories, but this is kind of really from pre-reading to reading. There, as I said, other groups that are also looking at OR-based measures. This is an activation measure, right inferior frontal cortex. Essentially, the core story is that you do get a prediction over, essentially, during adolescence, which children recover their reading and which children do not recover their reading. This work by Prof and colleagues, and it's very nice because it shows you that sometimes the right hemisphere activation has also predictive value. And finally, we have done, I think, the first attempt to look at multimodal prediction, and we found that if you combine the left occipital differential response in our simple string paradigm plus the EEG activity, the event-related potential showing discrimination between words and symbol strings, we get really quite good prediction if we take these two modalities. So in this case, the two methods are not fully converging, but they're complementary and really improving prediction. And I think that's also one way to go to look at prediction using multimodal imaging. This is another prediction story where we can show that essentially right hemisphere activity, this is why I show that right hemispheric specialization for print at a very early level leads to better prediction than with behavioral measures alone. And again, brain activity from kindergarten predicting reading performance in first grade in this case. So here are my summary points. I do think that essentially we can demonstrate that the reading brain develops, and we can also demonstrate how it develops by making links, by some form of plasticity, and we can illustrate this type of plasticity in specific networks at specific times within dynamics. We can also show that we can shape essentially this link. We can accelerate it or get it to work before formal reading training. And we can also see that the two imaging modalities really help us to get a clearer picture. Sometimes they really fully converge, like right at the beginning when you're fresh, when you're really starting to learn to read, but afterwards they diverge and emphasize different aspects. In terms of dyslexia, we focused on showing that print tuning is really reduced in dyslexia, that our core marker of print tuning, the electrophysiological one, indicates some normalization, but if you look in more detail, you find that there is no real normalization, and some smaller regions still show similar deficits. But we also see that later on, different connectivities, different phonological processing abilities, different processes when you do rapid string processing, and different processes during sentence reading become more important than this coarse visual print tuning. And in terms of outlook and perspectives, I can say, I've seen many interesting suggestions what to do, many great plans that you have and that you have in your center. And I think it's really important that we do focus on this brain-based approach. I think it's really advancing not only our scientific understanding, but it will also help us to devise really rational treatments. I think it's important that we stick to longitudinal designs and that we start looking early. I think multimodal imaging is a complication in a way, but it really helps to really understand the physiology and also the link to genetics and the link to essentially really basic physiological mechanisms and how circuits are really impaired and how training can kind of improve, normalize, or compensate for these deficits. And I think one way to go is, as many of us are doing, really go to look now at more individualized profiles to see really what an individual patient, or at least in a subgroup, what is really impaired, which circuit, which functions are impaired, and also to devise individualized training based on these insights. Thank you very much for your
We have exactly 1 minute, so if there are any short questions, if not at the end of the session, we'll have a longer discussion. Everybody's got questions. We'll have 3 questions.
And then
Okay.
someone else, I'll ask you.
I will ask later, maybe somebody else. I will give my turn.
I would like to ask you, you know that there are systems that give the children chance not to write, only to read. And in your conclusion, you find the GG, the game graphic, cause a very good development. So do you think, are you agree that it's better to continue to give them to write and not say they can print on any case and not try to write and read together?
I have to say I don't fully understand the question. So
I said that there are some system now that said the dyslexic children, you can let them free not to write by themselves, only to print.
okay, so
למה?
no handwriting or
אבל
what?
זה יצא בממצא שלו, תסתכלי. You
I
found that GG, the games, graphical games, make the children that there is for a correlation with phonology.
It's not a graphic game, Sarah. It's a grapho game, something
Okay.
different. You're mistaken. זה משהו אחר, Sarah.
Yeah, thank you. I think that's a simple misunderstanding. The game we showed is really it's really a matching game. Essentially,
Only
they have to
matching?
match the speech sound to a
Ah,
displayed letter. Okay, so I cannot say anything about writing because we didn't study that. Very interesting topic, but I have no data and
I think it was
no
misunderstood.
evidence. Yes, thank you for clarifying that. Yes.
Yes.
Okay. Quick question about the connectivity. You mentioned the connectivity, that you measure the connectivity between the word form area and the language network. Can you elaborate on what you mean by connectivity? Because I didn't see exactly the flow of the connectivity.
Okay, we simply did a functional connectivity analysis with bold data, and what that simply means is you look at a correlation of
Correlation. Okay.
the correlation with the
So there is no
different
directionality
regions.
actually.
Sorry?
So you actually don't have any information about the directionality of the connection.
No,
Okay.
no Granger causality, no sophisticated analysis, no DTI basis.
Okay, thank you.
Although I'm sure it's there, but we didn't do it.
Sure.
Thank you very much.